Welcome to the lecture on design of tubular truss member subjected to axial force. Before doing any member design, the analysis of the truss has to be completed. To analyze a truss, the loads on the truss has to be identified. For example, dead load, live load, wind load or any other loads if necessary. After identifying the load, do a load combination according to a standards. After identifying a governing load combination for the truss, do the analysis either by method of section or using any software. From the analysis, you came to know that what is the member force of the truss members. If the member force magnitudes are higher in magnitude, then consider rolled section as the member cross section. If the member forces are not that much high, it may be medium or low, then you go for tubular as the member. So here I'm going to explain how to do a tubular truss member of a tubular truss structure. Here I took a design of a bottom chord member. This bottom chord member is subjected to a maximum effect of 95 kilonewton with the nature of compression under the factored load combination of dead load and wind load. Then the same member is subject to a maximum tensile force of 100 kilonewton under a factored load combination of dead load and live load. So when you compare the member forces under two load combination, under one combination it is under tension and another combination is compression, and the tension magnitude is larger than the compression magnitude. Therefore, from this member force values, you should make a conclusion that the section has to be designed according to the maximum force and to be checked for the next predominant force. And the length of the member is said to be 2.2 meters. Here the problem also guides us to use medium class pipes and the grade of pipe is YST210. To know more about the class of the pipe and grade of steel pipe, please follow my earlier lecture that is on structural steel tube. This member subject to a tension of 100 kilonewton and a compression of 95 kilonewton. So I have taken a medium class and the grade of steel is 210. Why the medium sections are considered here is the common class of pipes are the medium class, and the common grade of pipe is also YST 210. Therefore, in this problem, I am using that basic or common form of pipes. To design a cross section, I have to do a trial section. To do a trial section, the IS 800 2007 Table 7 gives a guidance of limiting slenderness ratio. That means for a tension member in which a reversal of direct stress occurred due to loads other than wind or seismic force are said to be 180 kilonewton. With this guidelines, I'm going to calculate what is the radius of gyration. I can make a first trial case. Though the truss is pin connected, the K value taken is 1. I know the length of the member from which I calculate what is my radius of gyration. My radius of gyration is said to be or calculated as 12.2. So here it gives a clue that I can go for a trial section where my radius of gyration should not go beyond 12.22. To get a trial section, I should refer IS 1161 2014, where I took a trial section of 110 size, where 110 represents the nominal bore hole, that is internal diameter of the tube. The 127 is said to be the extra outside diameter of the tube. Here there are three classes based upon the wall thickness. This is a light class, medium class and heavy class. Since the problem advises us to go for medium class, therefore the thickness of the pipe is said to be 4.8. and the other details are to be taken for this medium cross. The designation of the pipe for this force is said to be ST 110 by 4.8. That means steel tube of internal diameter, that is nominal bore diameter of 110 with the medium cross, and grade of steel is 210. With this code guidance, I took all the necessary suction properties. In addition to, I should also take the yield stress of the pipe and the ultimate stress of the pipe. To design against tension, the design says that it has to be checked against three criteria. One is yielding of gross cross section, rupture at critical cross section, and block shear failure. To design against tension, first I am checking the gross cross section, yielding of gross cross section. So this is the condition given in your IS 800. So I'm substituting gross area of cross section, yield stress, and your partial safety factor. You will get the yielding capacity as this much. Here it is found to be, it is greater than your force actually acting on the cross section. Then the second criteria is rupture at critical cross section, where I have taken this expression because this is suitable for all rolled sections. It may be an open section like angle, channel or eye. It's also suitable for rolled closed section also. So this expression says that the capacity of the cross section under rupture is said to be the sum of the force of connected element plus the outstand element. The outstand elements is going to be influenced by a shear factor called beta, that is a shear lag factor. So that is expressed by this expression. It has an upper limit and lower limit. So to calculate this shear lag effect parameter, I should know what is the length of the connection. Therefore, first I'll do the connection design. Here I consider to do a connection in a tube. There are various form of connections are available in the construction industry. The tubes has to be connected to directly on the other tube, or otherwise a gusset plate could be used for connection. Here in this problem, I consider the pipe has to be connected to a gusset plate, and the gusset plate has to be connected to another member. So to connect such a gusset plate into the tube, the gusset plates are inserted at the mid diameter of the pipe to a length of say this much. So this is estimated based upon the length of the weld required to withstand the tension going to come in the pipe. So since the gusset plate is placed at the mid diameter, the pipe has to be connected to the gusset plate at 4 lengths of this much. Therefore, I am going to calculate how much will be the length of the weld and what will be the size of the weld to take this tensile capacity. So here, to do that, I should take some basic weld parameters. Say the ultimate stress of the weld is 14 MPa. The size of the weld is 5 mm. This is taken based upon the section 10 of IS 800. And the throat thickness has to be calculated. To calculate the throat thickness, I should see to it what is the angle between the two legs. Here this is a gusset plate and this is a pipe. So automatically the length need not be a 90-degree inclination, it is more than 90-degree. Therefore, in this particular problem, I consider the angle between the two legs are 91 degrees to 100 degrees. Therefore, the K parameter for the calculation of effective throat thickness is said to be 0.65. So here, therefore, the throat thickness will be 0.65 times the S. Taking this into account, I calculate the strength of the weld. So in the calculation of the strength of the weld, I consider the length of the weld is unit. Therefore, I got the capacity of the weld per unit run. Taking that as my strength of the weld, I know what is the force coming on the pipe divided by the strength of the weld. I'll get the size of the weld, that is the total cumulative length of this weld. I want to know what is the length of one length. Therefore, I am dividing by 1 by 4. I get the value will be 23. But this length going to be very critical in transferring the load from the pipe to the gusset plate. Therefore, after having a number of trials, I came to know that the size of the weld is approximately 3 times the size required. So when I'm explaining the block shear failure, you should know what is the importance of this length of the weld. Therefore, I am taking the length of the weld is 75 on one side. For such 75 has to be carried out to ensure the connection against a rupture. After knowing the wealth, I should calculate the beta parameter. To get this beta parameter, you should know all the parameters. Where W is the outstand length, this is the BS is the length of the outstand from the connection. Here, since it is welded, the outstand length as well as BS are one and the same. And you know what is the yield stress of the pipe, ultimate stress of the pipe, where LW1 is nothing but length of the pipe. Here we have calculated the length of the weld required for this connection is 75 I'm going to substitute that 75 here. Then I can calculate what is the value of beta. So the value of beta is coming like this. So from this we know that the value should not be more than these two limiting value. So it should not be greater than 1 and it should not be less than 0.7. Therefore, since it is very small, I am taking the minimum value of 0.7 and then I am calculating what is the capacity against rupture. And it was found that this is greater than the tension coming on the pipe. Then I'm going for block shear calculation. This is the expression given in IS 800 against block shear failure check. So to know about this expression says that there are two expressions. That is, when you check for block shear failure, like at that connection end, some of the portion are under shear and some of them are on tension. Now I'll explain that shear area and tension area. Since the pipe is pulling out from the gusset plate, this length, that is about the 4 lengths, the pipe is under, or the pipe cross section with respect to gusset is under shear. And at this end, that is the here, what happens is here the pipe has to be returned here. The end, the fillet has to be returned at this particular point. So at this junction, it is under tension. So by knowing the shear area and tension area, I'm going to calculate the shear area, where the gross shear area is nothing but length of the weld into the throat thickness. This is the effective area where the shear is going to experience. So that the shear area here, since it is a welded connection, net area is equal to gross area. In this problem, I consider the gusset plate thickness as 12 then the area of the tension. Here the tension means here the weld, here what happened, the weld has to be returned like this. So the pipe at this end, it has to be returned to minimum amount. Please check your section 10 about the return of weld. So where the area of weld under tension is thickness of the throat thickness into the thickness of the gusset plate, you will get the gusset plate thickness. So you will get what is the tension area. Again, since it's a welded connection, net area is equal to gross area. By considering these areas and substituting in this expression, since both are gross area, so I calculate the block shear capacity of the section, and it is found to be 114.91. As I told that if the length of the weld is going to be the predominant point in resisting the uh, cross section against block shear failure. If the length of the weld gets reduced, then it fails in a very low capacity. Therefore, here the length of the weld becomes very important. So from which I came to know that this is about 114.9 kilonewton, which is also greater than your tensile force. Now I am going to check the adequacy of the same cross section against compression. According to section 7, it is well known that to calculate the capacity against compression, you have to multiply the cross section area of the cross section with the design compressive stress. So to calculate the design compressive stress, you have to follow the following steps. Before that, we know that what is the compression is expected on the cross section and the radius of gyration of your cross section. So before going for the calculating the design capacity, we should check what will be the class of the cross section. So according to case 800 2007, table number 2 gives the guidelines to classify your cross section. So if it is a circular tubular section or welded tubes subjected to axial compression, your D by T ratio should be checked against 88 epsilon square. So if it is less than 88 epsilon square, then it is said to be semi-compact class. Then after calculating the D by T ratio, where D is nothing but outside diameter, where T is nothing but thickness of the wall, then you know what is the D by T ratio. It is less than 88, where epsilon is nothing but 1 here for our case. Then if it is semi-compact, then we go for the calculation of the designed compressive stress of this particular tube section. To calculate that, we have to calculate the FCC, where FCC is nothing but pi squared E by the KL by R the whole square. So already we know that what is your KL by R square. Then you calculate what is your, because you know what is your K, what is your L and what is your R, everything. Young's modulus is also know. You calculate what is your FCC. Then if you substitute it here, you will get the non-dimensional slenderness ratio as 0.525. Then you have to know the buckling clause of your particular tube section. According to the clause IS 800 2007 and table number 10, you know that for hollow circular or non-circular section, for hot rolled case and cold formed case, this is classified to A or B. Here in this problem, I consider the tube is a hot rolled section. Therefore, my buckling class will be A. So if I know the buckling class A, then from the table of this coefficient, I know that what is the alpha coefficient, that is imperfection factor, where which is said to be 0.21. If I know the slenderness ratio and imperfection factor, I will able to calculate the intermediate value phi. If I know the intermediate value phi and I calculate the strength reduction factor chi will be equal to 0.915. This should be always less than 1. If I know the value of chi, I should calculate what is FCD. If FCD is known, that is 175 approximately, then you multiply the area of cross section. The capacity is found to be 322. It is very safe against your compression. Therefore, here for this bottom chord member, the pipe of designation ST 110 by 4.8 YST 210 is safe for both under tension as well as compression. Thank you.